make a call from a mobile phone, sometimes we can connect and sometimes we cannot. If we are in the basement of a region, we cannot connect. Or if we are under a tree, sometimes it doesn't connect. Or we are moving at a very high speed in a train, we cannot connect. What is that changes? Changes is the channel of the wireless communication system. What if we can estimate the channel and undo its effect? That's what we are going to learn in this lecture. Welcome to my channel Engineering Knowledge. In this lecture, I will discuss about channel estimation basics and why it is important and how we can do it in a very simple way. Do watch the video till end to grab all the information. So let us start and see how we can estimate wireless channels. Before doing that, let us see what is a wireless channel. So a wireless channel is basically the resultant of a very complex phenomenon in which the signal is carried out through an electromagnetic wave. There are base stations which communicate with users and users communicate with base station. There are various towers. The system is pretty much very mobile. Various vehicles travel there, and it consists of very dense populated buildings, trees, and every other kind of foliage. The signals that travel are actually due to three phenomena. The phenomena that govern the transmission of signals. The first one is called reflection. The second one is called diffraction. The third one is called scattering. In reflection, the wavelength of the EM wave is smaller than the dimension of obstruction. When the signals undergo the sharp edges, then this is called diffraction. They impinge on the sharp edges of various buildings. The scattering is the phenomenon in which the EM waves wavelength is very large compared to the obstruction. So basically, these three phenomena give rise to what is called the multipath fading. Apart from that, in any mobile communication system, we also have provision of mobility of various entities, and this brings in a shift in the carrier frequency that is due to the relative motion of various devices, and this term is called the Doppler's effect. So basically, whenever we want to model a wireless communication system, the wireless channel which takes the information itself is a very complex entity, and it depends on the multipath fading and Doppler's effect. So therefore, uh, we model the multipath propagation in one of my videos in this channel. We have discussed that we take the ith channel component such that it has an amplitude of ai and a delay of tau y, which means that ai delta t minus tau y. The ith channel component comprises of an attenuation factor of ai and a delay of tau y, and all the copies combine constructively or destructively, giving rise to uh, this equation, that is ht. The impulse response of the channel is summation of I is equal to 1 to n hit, which means summation I is equal to 1 to n ai delta t minus tau y. So this is basically the representation of wireless communication channel. We can also see that with this representation, if we want to estimate the channel, first of all we will apply what is called the narrowband approximation. In the narrowband approximation, we consider that there is only flat fading. Flat fading means the coherence bandwidth of the channel is larger than the bandwidth of the symbol that is being transmitted, and therefore the symbol, which is xb of t minus tau y, the delayed form of the symbol, can be approximated as xb of t, and then the received signal yb of t is basically h into x. H, we have replaced the multipath component, and therefore this is my h, which is basically I is equal to 1 to n ai e raised to the power minus j complex exponential e raised to the power minus j 2 pi fc tau I. Here there are three entities in this channel. The first entity is the carrier frequency f suffix c. The second entity is the delay, and the third entity is the amplitude, which is basically attenuation, because when all ais will be smaller than 1. So this is how typically we represent a wireless communication channel. If we want to mathematically evaluate this channel H, then we use some statistical models and we use the probability density functions in such a way that like we use relay models, statistical models, for example relay models. So relay fading is used generally when there is a severe case of fading, and a very easily mathematically tractable model that we apply is relay fading. A slightly modified version of relay fading is Nakagami M fading, where there is an M parameter. If M is equal to 1, it becomes relay fading. Otherwise, for M between zero point 0.5 to 1, it gives more severe case of fading. And for larger values of 1, M larger than 1, it gives us a fading which is less severe as compared to relay fading. If there is a line of sight component, then we use what is called a Raysian model. Other than that, there are several other models, not limiting to K distribution. So there are very other models also. So these statistical models can be used to analyze the channel. But why this channel estimation is important? Because once we know the channel, we can actually accurately detect the data because we know the channel response, so we can recover the transmitted symbols correctly. Also, we can apply equalization. What is equalization? Is to undo the things that have been done in the channel. How do we undo? We multiply by 1 by h. So if our 1 by h is accurately equal to h, then h into 1 by h becomes 1. And therefore, we totally negate whatever fading has been done in the communication channel. That's not possible. But then there are other equalizers like zero forcing or MMSE. And this is only possible when we have a perfect estimation of the channel. We can improve the capacity of the channel using this, or we can perform resource allocation. This is very important, resource allocation. Once we know the channel state information is basically the fading channel. If we know the channel, if we have the CSI values, we can know that which part of the wireless communication system is undergoing severe fading. Where there is severe fading, there is no meaning of assigning more number of resources in that block, and therefore we will assign less resource to a block undergoing severe fading, and vice versa. Which means whenever the communication system channel will have favorable conditions, we will assign more number of resources at that place, and therefore resource allocation also becomes very critical and very helpful when we have the channel estimation. But how it is done actually? It is done that by using field measurements, in which there is a wireless RF engineer that takes its set, revolves around the park and measures RSSI. And this phenomenon, you can understand, is very cumbersome. It's not applicable every time, and it involves manpower, time loss, and it is just waste of man management. And therefore, mathematically in research, it is of prime importance that we can facilitate a solution which is not like this. And for that, we model the wireless system signal flow. Here what we assume is that there is a user that sends or receives signal on the wireless medium. We want to predict what is the medium, understand this. So there is a wireless user, he wants to communicate with the base station on a wireless link. The wireless link undergoes severe fading, and there is a wireless fading. And apart from fading, one other entity that exists is known as the noise. We generally model it as additive white Gaussian noise, AWGN. Other than that, you can understand that there is also an applicability of noise. So if we see this noise, uh, so X is the information that we want to send through the channel, which is denoted by H, and there is a noise component of N, then the received signal is at the base station BTS as given as Y. So what is Y? Y is basically X into H plus N. Basically, this is the channel multiplied by X. We wrote the equation previous also, XB into H, and H was summation of I. So this is the narrow band channel that we want to predict, plus the additive white Gaussian noise N. So what is important here, the most important thing is that h is the fading coefficient. The fading coefficient h and the n are both random in nature. What is meant by being random in nature? It means that they can only be described in terms of statistical models. They cannot be described deterministically. So we only have deterministic compositions of y and x, but y is basically made up of x into h plus n, where n and h both are random in nature, and therefore we cannot determine the points directly. So then how do we estimate? The estimation becomes very easy. We send a pilot signal on the wireless medium. When this signal is received, pilot signal is like before starting the actual conversation, we send some bits to check how the channel is responding. We measure y is equal to xh plus n. Now for simplicity, this is a very simple model, least square model. We assume that there is no noise. So if there is no noise, our equation becomes y is equal to x into h hat, where h hat is basically an estimated value of h. So this can be written as h hat is equal to y upon x, the ratio of y upon x. So if we look at this h hat will not never be equal to h. There will be an approximate error between h bar and h. That can be written as E is equal to h minus h bar. This is the channel estimation error. This channel estimation error is basically a difference between the actual fading coefficient and h hat bar. Now, then this method is actually known as least square channel estimation, which is to find the channel uh, fading coefficient h hat that minimizes the squared error h minus h hat whole square. So basically, this the error and its square. Why we taking square? Because h minus h hat is the difference between the estimated value and the actual value. Where the estimated value is h hat and actual value is h. Its a square will not take the sign because we are not interested in how far positive or negative it is. We are interested in how far the difference is. So if we minimize this, then this scheme is called least square. In least square, the h hat is given by the ratio of y upon x. If we go in more complex mathematics, I'm not going there, but in matrix form, if we have symbols x as an array and y as an array, we will have h hat, the estimated value, using the least square method as s x raised to the s, where xh is basically Hermitian operator over the symbol matrix x into x inverse into x Hermitian into y. So this is all for this lecture. Thank you, and do subscribe and like the channel to support my work. Thank you.